Happy to welcome back a familiar face. Leonardo Rastelli is back again to this time as an official candidate, and he's going to tell us about charting the space of superconformal field theories.
Thank you very much. It's a pleasure to be back. So I will give a somewhat more focused version of the talk that I gave in January. I felt that given that this is a smaller room and a smaller audience, I was entitled to make it more focused. So there will still be a somewhat broad introduction. I'll try to put things in perspective about the conceptual nature of our enterprise, but it will be it will have a more direct focus on my recent work and also some of my not so recent work. In fact, I view what I'm doing now as sort of an outgrowth of the work that I did previously on superconformal indices, and so there's a long list of excellent collaborators that are acknowledged here, and you have met some of them recently. So, I will spare you, although perhaps not entirely. Let me at least start with some couple of sentences. Perhaps I do not really need to motivate to this audience why conformal field theory is important. It describes pretty much all of fundamental physics except gravity, and it also describes a large amount of interesting condensed matter physics and statistical mechanics. For example, the theory of phase transitions and many body systems. And so our viewpoint today will be try to explore the deeper structure of quantum field theory. And I will start with a very basic reminder, 30 seconds introduction to quantum field theory. There are local fields, phi of x. X is a point in space-time if you're doing particle physics, or in space if you're doing statistical mechanics. Going back and forth between the two formalisms, at least to a physicist's satisfaction, is rather easy. You continue time from imaginary to real, and here I'm using the conventions where everything is being Euclideanized, so there's a minus sign in the measure. And there is a local action, which is a local function of the fields, and a factor 1 over h bar that tells us that the classical limit in which we can do saddle point approximation h bar going to 0. Now we can handle this infinite dimensional integral, which defines the theory, this infinite dimensional functional integral, either formally, if we do perturbation theories in power of h bar, or more directly, if we discretize space-time, for example, by taking x to lie on a lattice and taking the continuum limit. In both approaches, you really need to make sense of this infinite dimensional integral. You need to be careful, and so taking the continuum limit, for example, starting from the lattice, requires a certain sophistication, and that's a subject of normalization theory. But by now, after let's say 80 or 90 years, we are more or less understand what to do. And although not every step in this procedure has been defined to the satisfaction of a mathematician, in many cases we really think we know how to handle this kind of infinite dimensional integrals. And the result is very useful. It allows us to describe an enormous amount of physical phenomena. So, as I was mentioning, the easy part of the problem is dealing with that infinite dimensional integral in a semiclassical expansion, and let me remind you how that goes. This action is a local functional, so it's an integral of space-time of some local function of the field that we have a kinetic term and then tower of interactions, and the nonlinearities are parameterized by some coupling constant G, And when G goes to 0, we can do perturbation theory. This is the familiar subject of Feynman diagrammatics. And there is a textbook little argument, this quantum field theory 101. The weak coupling expansion really is the same as the classical limit, because by triggering scaling of the field, you can pull out an overall factor of G square H bar, and so expanding in G square really is the same as expanding in H bar. And so we should understand perturbation theory as a semiclassical limit. In more sophisticated applications, you also need to take into account other non-perturbative saddles, such as instantons or trivial field configurations, but it's a very well understood story of how to take the semiclassical expansion of this integral. On the other hand, you often face in phase situations where the coupling is not small, and then tools are much less under control. You could try like simulations, they work for certain observables, not for everything, and generally how to even make sense of this infinite dimensional thing is much less understood. So, from this very quick reminder of, which really you certainly didn't understand it from this if you didn't know it before, but it was meant as a reminder of the formalism of quantum field theory, one may get the impression, which is of course the impression you get in any standard course or reading any standard textbook, that quantum field theory is about writing Lagrangians, enumerating the fields that appear in the Lagrangian, enumerating the possible interactions that appear in your Lagrangian. In fact, it's quite easy to classify all possible Lagrangians that have a well-defined perturbative expansion. These are the so-called normalizable field theories. And you may think that that's the heart of the subject. And for some purposes it is, but today I would like to challenge this basic paradigm and expose you to some discoveries which admittedly are mostly confined to supersymmetric field theories in various space-time dimensions, where this is not, in fact, the most appropriate or even the most efficient framework. And I really saying this from the outset, supersymmetry will be a crucial technical ingredient for us, but my viewpoint is that although supersymmetry is important to analytic control, I believe the conceptual lessons are completely general. So let me present you with some sort of evidence or revisionist history, if you will, of why this approach based on explicit fields that you write Lagrangians with is inadequate. And so, evidence. The first item that I'd like to emphasize is the role of non-perturbative dualities. So there are by now many examples, and again, certainly in space-time dimension, the two supersymmetries of crucial help in making these examples tractable. But we now have many examples of pairs of theories in the following sense. You have a theory defined by a certain set of elementary fields. I'm being a little schematic here with some coupling constant G, perhaps several couplings. And a theory T prime defined by an a priori different set of fields phi prime with a different set of couplings. And again, schematically, the two theories are completely equivalent. All the physical observables you can compute in either are the same, up to a redefinition of the coupling such that when the first theory is weakly coupled, as G goes to 0, the second one is strongly coupled and vice versa. Now, it is perhaps not quite right to say that these are two different theories defined by a set of field phi, set of field phi prime. If you remember what I told you a slide ago, namely that one should really understand the weak coupling limit as a semiclassical limit. So a better way to describe the situation is to say that there is only one theory. Fundamentally, there's only one theory we are describing, but we are describing a theory that has two semiclassical limits. In one semiclassical limit, these degrees of freedom described by the first set of fields is weakly coupled. In the other semiclassical limit, a priori different set of fields is weakly coupled. And so by now we have a variety of situations where this is understood. In some even more special cases, the theory is self-dual. It so happens to be the case that the same set of fields appear in both a weak and strong coupling, but with a complicated nonlinear definition. In other cases, the theories are completely different-looking. And so at the very least, you should now start questioning the paradigm that says the fields are the fundamental way to think about field theory, because clearly this one intrinsic quantum theory is neither described by phi prime, is described by either both or neither. It's something more fundamental than both set of fields. And even more striking, and this is the lesson that I think at deep conceptual level we are still absorbing now, that started with the discovery of the gauge gravity duality in the late 90s. It turns out that in some cases, some quantum field theories with no gravity have a dual description in terms of theories that contain gravity, except that the theory containing gravity lives in higher number of space-time dimensions. And so gauge symmetries such as diffeomorphism invariance, or in some cases it could be the case that the field phi has a regular gauge symmetry and the field phi prime has no gauge symmetry or different type of gauge symmetry. And even the number of space-time dimensions are not really fundamental to the definition of quantum field theory.
Would it be fair to say that the moment we had written the path integral, then in a sense what you say was obvious, because the fields were just integration variables?
Yeah, maybe. But the way you write observables is in terms of function of the fields, and so
things as a particle equals field.
And so in our usual way of thinking, we have at least instinct to identify the fundamental fields with the weakly coupled degrees of freedom. Of course, as physicists, we know very well that that's not always.
But in a way to continue perhaps your own argument, if I understand correctly, you're basically saying we got lucky that such simple identifications of observables in terms of constructions involving relatively simple expressions of fields happen to work in some of the cases in weak coupling.
Well, in fact, it happens to work extremely well, as you know, for
exactly,
physics. In fact, it works embarrassingly well. We would love to see some strong coupling at the LHC, and we say we're just seeing a bunch of...
And then you're saying it's basically a knee-jerk reaction just because of that simplicity and efficiency to basically promote fields into fundamental...
well, we have of course another paradigm which is goes counter what you just said, which is QCD. In QCD, that's of course not the case. In QCD, the Lagrangian is written in terms of gluons, and then there the situation is somewhat mixed because at high energy those are the polar degrees of freedom, but they're not at low energy. So of course, I'm sorry, perhaps I don't want to present this as my own wisdom. This is the wisdom accumulated over decades of intuition and quantum field theory, and so I'm certainly aware that a large portion of the audience shares much of this intuition.
So is it fair to say that in a sense the fundamental question is really how to define observables if we don't know fields in weak coupling? Is that in a
well, to me, and I will come to it in the second part of the talk, and of course that's of course not a new idea either. Indeed, you need to take a step back and formulate the question in terms of what is observable. And so that could be the S matrix for certain type of questions, or correlation functions of gauge invariant local operator for certain other type of question situations. And if you formulate everything in terms of what is strictly observable, then you can hope to have something which is more fundamental.
you also think about correlation functions of local operators. You have useful line to see.
That's right. Or that's right. Or that's very much a welcome enlargement of the framework. You can consider non-local operators as well. So a familiar example, well, familiar to I think many of you of duality is the duality that involves the maximally supersymmetric cousin of QCD, which is a theory in fourth space-time dimension, which has a long number of supersymmetries without having to include gravity, and that's known as n equals to 4. 4 counts the number of supersymmetries, Super-Yang-Mills theory. And there is a minor variation over the schematic framework of the previous slide. The coupling gets complexified, so tau is this imaginary unit divided by g squared plus a real phase. And so, given that g squared is a positive number, a priori this complexified coupling lives in the upper half complex plane. But in fact, by now we have overwhelming evidence, although certainly no proof, that the theory has an exact duality under SL2Z transformations of the coupling, in which the electric and magnetic variables are transformed by a 2x2 matrix involving this SL2Z transformation. And you see, what's going on here, this is a generalization of the basic G from 0 to infinity type of duality. If I set the angle to 0, one of these transformations would say that tau goes into minus 1 over tau, which says that G goes to 1 over G. And here's a picture of the upper half plane. If you mod out by these SL2Z transformations, then this gray region is a fundamental domain, and you can tessellate the whole plane with infinitely many copies of it. And so what a priori you thought was a strong coupling limit of the theory as G going to infinity here, this is the origin of the upper half plane, so G is infinity, in fact is mapped by the duality to the weakly coupled point in terms of reshuffling of the same fields. And so by the time you have modded out theory space, which is in this case parameterized by the complexified gauge coupling, by this SL2D transformation, you have a region where there are no strong coupling points at all. The strong coupling regions have been excised from theory space. And I think a very good reminder of how inadequate the path integral formulation of field theory is that nobody has any idea, not the slightest idea, of how to prove such a fundamental and exact statement using path integrals.
But do you have in mind that such a path integral derivation in principle has to exist?
I think it should, right? I mean, there are. So let me first of all remind you in the sense, remind everybody. There is a very simple analog of this situation for abelian theories. For abelian theories, you can indeed give an exact derivation of S duality. And in fact, you can do that in the lattice version of the theory. This is a famous story. So in 2 dimensions, this is Kramer's duality. It's the duality of the Ising model to itself. And in 3 dimensions, the duality of lattice gauge theory to the lattice Ising model. And in 4 dimensions, there is, again, a duality of abelian lattice theory. So for an abelian theory, this makes perfect sense both in the continuous formulation and in the regulated lattice formulation. So I would expect, in fact, this is one of those one of those crazy research projects I never get to because I think they're too hard. People have given lattice formulations of n equals 4 Super-Yang-Mills, where they claim to preserve some supersymmetry, and they claim, in fact, that the entire supersymmetry is recovered in the continuous limit. So if you want a great research project, take that lattice theory and try to prove S duality by a lattice change of variables. Obviously, it's incredibly hard. But yes, I do think that in the appropriate regulated version, which would have to presumably some sort of lattice theory, such a patented observation should exist, but it's extremely hard.
So how is it proven? I mean, if it's not by patent.
So it's not proven. It's accumulated evidence over the years. You can go to the so this is a long story. We can talk about it later, but we have by now an enormous amount of indirect evidence because you can compute a variety of protected quantities, both for the theories for the theory at the superconformal point, the theory in the Coulomb branch, that agree with this basic statement. Also, this is not going to convince you, but string theory, which is a much less understood framework than quantum field theory, predicts the duality in a certain decoupling unit.
But you could say protected, right?
Sorry?
So if you went, is there any example of when you say protected, you meant by super?
So to the best of my knowledge, the only paper that even addresses the issue of S duality and non-perturbative, etc., is my paper on the superconformal booster very conformal pyramids.
And what do you conclude?
Conclusions are murky because everything is numerical, but we do have circumstantial evidence that it's a bit of an indirect argument, that the bounds that we obtain from the bootstrap are compatible with S duality by a certain Padera summation participation theory. So it's numerical, very tentative, but at least it's a kind of framework that would allow you to address the question. Okay, so at the very least, this field theory viewpoint does not easily allow for a description of dualities. They are quite hidden at best. But in fact, things get worse because we have now a relatively long list and growing and fundamental, as I will argue momentarily, of theories that appear to have no Lagrangian formulation whatsoever. So one theory that has been at the center of many recent developments is this six-dimensional theory, which was originally discovered in the context of string theory. In fact, its simplest definition is a theory that governs the low-energy fluctuations of these rather exotic objects. These are five-dimensional membranes. 5 dimensions refers to the number of space-like directions, and then there's time. So all in all, it's 5 plus 1, 6 space-time dimensions. So these are the most mysterious objects, I would argue, in string theory. In fact, they are solitonic objects in 11 dimensions. And if you take a stack of n of them on top of each other, you have a complicated interacting quantum field theory, which decouples from gravity in the low energy limit. And we don't really have a very good name for it. We call it, with this rather ugly symbol, 2-0, because that's the name of the superconformal algebra under which the theory is invariant. It means that there are two supersymmetries of one chirality and 0 of the other. And in fact, you can take this definition or attempt at a definition as the low energy limit of n5 branes to further provide you with a discrete parameter n. But this theory has no continuous coupling. There's no analog of the G that I had in previous slides. In fact, I could alternatively say that G is equal to 1. You are intrinsically strongly coupled regime. Or if you wish, H bar is set to 1. There's no semiclassical expansion of the theory for finite n. Something very remarkable happens for large n. For large n, the theory does have a semiclassical limit, and in fact it becomes equivalent by one of these magical duality relating quantum field theories to gravitational theories to classical 11-dimensional supergravity compactified on this space, which is the product of the maximally symmetric negative curvature space in 7 dimensions, which is the ADS7, and the force field. Now, so this description is only valid for large n, and it is not known, even in principle, how to compute systematically one of our corrections on this side, because that would amount to having a definition of quantum end theory, which is one of the research projects for the 21st century. Yes.
So, I'm still confused about this. When you say this is a non-Lagrangian quantum field theory, what you mean is just we don't know how to write a Lagrangian for it? I mean, we
in
can
this
do
case,
path
in this
integrals,
case,
we
in
can
this
do
case,
path
I say
integrals,
something. I mean actually something a little bit worse.
Okay.
That I don't even know in principle how a Lagrangian six dimension could ever look like, because in six dimension, at least not under the standard rules of Wilsonian field theory. Because in 6 dimensions, just by power counting, there's no way you could write down a normalizable interaction that would make sense. And so your best hope would be to write down a Lagrangian with the non-normalizable interactions and hope to get this field theory as a UV fixed point. Maybe. Maybe that's in the realm of possibilities, but good luck with that.
So to ask a different way, can I exchange the word non-Lagrangian for non-path integral?
You could. Non-Lagrangian,
Same thing.
yes. Yes, I'm sorry, there's a question.
So this n and the number of quantities is unrelated to symmetry in general and in particular to gauge symmetry?
Well, we think at some deep level it may have to do something with some two-form type of gauge symmetry. So, okay, so there are many things are known about this theory, which are all very mysterious. One way you may hope to understand what's happening a little bit better is by separating the brane slightly. If you separate the brane slightly, then you are dealing with a collection of abelian theories plus higher terms that come from the off-diagonal interactions of the branes. Each abelian theory is something that, although a purist may say it doesn't have a Lagrangian description because of some self-dual condition on a two-form, I would say, for my purpose, it has a perfectly good field theoretic definition. But then you have these off-diagonal degrees of freedom that in the M-theory picture correspond to stretch membranes between the M5 branes. And in the limit in which, on the Ward volume of the M5 brane, these are string-like degrees of freedom. So in the regime which the one of interest to us, where these branes coincide, you have some string-like non-abelian degrees of freedom of the Ward volume. So it's not something that can be described in any obvious sense by a particle, by the kind of local field that we normally associate with particle. It's some string-like excitation. So that's the best that I can offer. And people still, to this day, I mean, there's a large industry, well, maybe not, perhaps not a large industry. There is a bit of an industry in attempting to write down some sort of Lagrangian, but everybody will agree that nobody will ever be able to write down a perfectly local Lorentz-Lagrangian six dimension. Best you can hope for some like cone story or some compactified story where you trade the inevitable non-locality with the lack of fully manifest Lorentz invariance. But I'm not very optimistic about any such attempt.
So the D equals 6 should have signature 5, 1 in principle, right? So it has a time-like killing vector.
Yes.
So suppose I should be able to write down some kind of Hamiltonian generator and exponentiate the time split it. That may look very non-local or something. Is that the issue? Or?
Be my guest.
But in principle, it should be good.
Well, I mean, if all you're saying is that we are going to have a Hamiltonian formulation in terms of some Hilbert space with a Hamiltonian, sure, but the point here is not just a total Hamiltonian, but to write down a local Hamiltonian, write down something which makes sense in terms of some fundamental degrees of freedom.
So to follow up on that, there's no stress tensor?
There is a stress tensor.
Well, then you've got a local.
Well, you do, but what is the Lagrangian formulation of? Well, the Lagrangian formulation of the Hamiltonian space is a Hamiltonian formulation. So you have some Hamiltonian formulation in terms of some fundamental degrees of freedom. but you don't have local fields. I don't know how to rephrase it. They have local fields you can integrate in a path integral.
Is it better to say that you know the correlators of the stress tensor? That's
You
the
certainly know the correlators
that's
of the stress
sense in which
tensor.
you have a stress tensor, not in the sense of having a stress tensor in terms of local field.
You have a stress tensor in the sense of you have a generator of conformal transformations, and you can compute correlation functions of it with other local operators, but no intrinsic fundamental field. Now, 6 dimensions may be exotic for you, so what about 4 dimensions?
Sorry, just one more question.
Yes.
So,
This is, by the way,
You're
I'm just reviewing the lore, so this is not yet my work, but I'm
sorry.
welcome to.
So if you have the fields you're going to compute the correlators of, and if you have a local stress tensor, then what you're saying is you just haven't figured out a way, I don't mean you personally, but haven't figured out a way to write the stress tensor in terms of those fields.
Yes, and I don't think there is such a way.
Okay.
There will never be. I cannot prove that there never will be. I mean, you can prove it. It's hard to prove a negative, but I think it would not. It seems to me that this is not the right way to think about this problem. Now, there is a other more, in some sense, even more exotic because of what I'm about to say, but in another sense, perhaps more palatable class of examples. They're more palatable because they are in 4 dimensions. So now this example arises the moment you take supersymmetry to be not the complete set, which is n equals to 4, but you take half of it, which is n equals to 2. And then you find a sequence of animals, again labeled by an integer n, which are denoted by this mythological figure with 3 legs. And that's incidentally the symbol of Sicily. And the 3 legs refer to the fact that the theory has this funny global symmetry, SUN times SUN times SUN. So this is known as a trinion theory. And you can use this beast, this new creature, as a building block. So you can now gauge this leg by coupling it to gauge fields and perhaps take another of these beasts and couple them together, much like you construct Lagrangian theories by gauging ordinary matter. Ordinary matter is something you can write down in Lagrangian. There are quarks, or for the aspects here, there are hypermultiplets in n equal to 2 theory. If you're willing to take this as a black box, you don't know what it is, you're not allowed to look inside. You just know that it's some strongly coupled beast with no intrinsic coupling. You can use as a building block for more complicated fields. Now, you may say, okay, I mean, is this really convincing? First you have 6 dimensions, then you have a marine monster with 3 legs. I mean, what is the meaning of this? May not sound like a very compelling case for abandonment of the field theory viewpoint, but in fact, you'll be quite mistaken because of the following phenomenon. And again, I'm giving you a little bit of a revisionist history because this phenomenon was discovered before the invention of this 3-legged monster. You take something very mundane, which is really one of the simplest things you could imagine. A theory with SU3 gauge group and 6 master quarks. Well, in fact, that's not too far from QCD, except that I want the n equal to 2 version of that. And remember this complexified coupling tau that I had earlier. Here it turns out that the same S duality that I had in n equal to 4 square bits is still there. But if you do things carefully, you discover that after you mod out by the standard S duality, you remain with a strongly coupled singularity that cannot be removed by standard dualities. And Argyris and Zeiberg argued in 2007 that this strongly coupled point has a weakly coupled description, or quote-unquote weakly coupled description, in terms of the beast I had earlier, the Tn theory for n equal to 3, coupled to some SU2 gauge fields. Now, the SU2 gauge fields are weakly coupled, But you have to allow for this new strongly coupled or new intrinsically quantum piece as part of the game. And in fact, there is a very real sense in which you start from perfectly ordinary looking garden variety Lagrangian field theory, you move in their moduli space of couplings, and inevitably you encounter these other beasts. And in fact, in a sense, the points where you have a conventional Lagrangian description in terms of path integral are measured zero set in the space of all possible theories. So these beasts are very much part of the landscape.
Why haven't you just told us that there is a Lagrangian description of this beast, that it's just strongly coupled Lagrangian
Because,
description?
well, that's playing with words. I mean,
I can do path integrals for a strongly coupled theory. I can stick them on a lattice.
I think it's deeper than that, for the following reason, that here you don't quite get this theory. You get this theory coupled to gauge fields.
Okay.
And so not everything in this theory will be accessible by the dual Lagrangian description. In particular, only certain gauge singlet set of this theory will be really accessible. And, I don't know, perhaps there's a disagreement on my choice of words. By Lagrangian description, I mean something I can do a semiclassical expansion with.
Okay.
And so, perhaps we should avoid this terminology, which is by now completely standard in our community of Lagrangian versus non-Lagrangian. We should use the word semiclassical expansion, and then everybody would agree that these theories have absolutely no semiclassical description. So what I'm going to do next, okay, so it seems then inevitable, both because these things exist and because they're pervasive, to do something a little different. And what I will advocate is a more abstract algebraic viewpoint. To study, again, you will have certainly appreciated that all the examples I had so far were not only supersymmetric, but in fact they enjoy conformal invariance. These will play a crucial role for me in the following. And those theories also had sufficient amount of symmetry that we can indeed hope that symmetry will completely fix them. And so that's the viewpoint that we will take. We will impose consistency under the full set of rules you may want to define a quantum field theory with. And the theory will be defined abstractly in terms of a set of correlation function. And we are hoping that these rules will be so restrictive as to fix the theory uniquely. That's the hope, that's the aspiration. So this is what is known as the bootstrap program, and I will describe it in a little bit more detail later on. And it's about the consistency of the abstract operator algebra in any individual theory. But towards the end, and I don't know if I will have much time on it, it's also slightly more subtle notion of consistency. I will describe another notion of quantum consistency, which is the fact that as we move in theory space, we should have consistency of these different semiclassical points under dualities. And that's also extremely powerful. Okay, so one slide summary of conformal field theory. So conformal field theories describe the asymptotic regimes of quantum field theory. So when energies are much smaller or much bigger than your intrinsic mass scales, you have approximate scale invariance. And similarly, when you have a statistical system near the critical point, the correlation length diverges, and so you gain an approximate scale invariance, which becomes exactly the critical point. And it has been the experience of physicists that these invariants under dilations, in fact, generically enhances to the full conformal group, which locally is like a dilation combined with a dilation. In fact, it has not been fully proved that this is the case, and there's a bit of an open debate under exact which conditions we can a conformal invariance to follow from scale invariance in 2 dimensions proved under some, first of all, the assumption of unitarity, there's some additional technical assumptions, but in higher dimensions still a bit of an open issue. But anyway, we'll take conformal field theory as our defining setup. And conformal field theories are, of course, a bit special because they describe the asymptotic regimes of quantum field theory, but perhaps not so special the moment we realize that a generic quantum field theory, this is the picture that in some sense is due to Wilson, should be viewed as a renormalization group flow between a UV and infrared conformal field theory. So again, you may by now be quite familiar with the viewpoint which is explained in this slide. I define a conformal field theory abstractly. I'm agnostic about its intrinsic fundamental degrees of freedom, if any, or intrinsic path integral, or semiclassical expansion, or not. This is a viewpoint which will be familiar to those of you who are versed in two-dimensional conformal field theory. It is there the more common and standard viewpoint. Rather, I take the set of local operators, and as Albert said, there's no reason why one could not enlarge a framework from local operators. It's, at this point, simply a matter of technical convenience.
As if you have non-local operators, you don't have a P, yeah?
Well, you have a more complicated OP, where, for example, you could take a say, codimension n operator with a local operator, and then as the local operator approaches the codimension n defect, there will be what's called a boundary operator product expansion, where you will generate excitations on the defect that can be understood as operators intrinsically on the defect, and you could develop the framework that has been developed to great effect for boundary conditions, for codimension 1 operators. This is an established framework, and for codimension 2 there's a bit of work, but it is certainly within the general framework allowed. So today, I'm willfully ignoring complications associated with non-local operators, and in fact also additional constraints that may come from putting the theory on trivial geometry. I'm just taking local operators on flat space. And so the theory is defined by the correlation function of a set of local operators, and it's convenient to use conformal representation theory to organize the operators in terms of what's called the primary operator, which cannot be written as a derivative of something else, and its infinite tower of space-time derivatives. Operators are characterized by their scaling dimension, and the crucial axiom is the operator product expansion. So two local operators can be expanded in an infinite set of operators, and it turns out that using this organization in conformal families, I only need to worry about the first term in this expansion, which tells me how two primaries give me a third primary, and the dots here are the contribution from the derivatives of this primary, which are completely fixed by conformal invariance. So the entire dynamical content of the theory is fixed in terms of conformal dimension and the 3-point couplings of the primaries. And it should be clear that by successive application to the operator product expansion, I decompose an n-point function to a 1-point function. The 1-point function is 0 unless the remaining operator is the identity, and so by knowing the spectrum of the theory, which is the set of conformal weights and the pre-coefficients, I know everything. Now, the crucial point here is this assumption that this is a true operator equation which converges inside correlators with a radius of conversion fixed by the next insertion point. And here is now the more technical significance of this word that has come up earlier on, which is the conformal bootstrap. The idea is to take a 4-point function and decompose it in two equivalent ways. First, by doing the OP of operator 1 and 2, and 3 and 4. Now, a priori, you get a infinite sum here and infinite sum there, but you can choose a base of operators where the operators are diagonal, and so that can reduce to a single sum. Similarly, if you fuse 1 and 3 first, you get another sum, but this is just associativity of the operator algebra. These two ways of expand must agree. You can prove, in fact, that there is a common region, a finite dimension region for the choice of the coordinates of the decimal operators where both sides absolutely converge. And I'm illustrating this here for the case of 4 identical operators, which I'm calling phi. Phi and phi go to operator OJ. Since the external operators are now the same, the sum here is equal to the sum there. And this special function g of u and v, where u and v are conformal invariant cross ratios, resounds a contribution not just of the primary OJ, but its infinite power of derivatives. These are known as the conformal blocks. And so the statement that this left-hand side is equal to the right-hand side is the statement that when you swap the external coordinates, when you swap 2 and 3, for example, which means swapping u and v, you get the same result. So this is an ancient idea that in fact goes back to the early 70s, Polyakov, Radalagatta, and Grillo, and this gentleman said, well, perhaps these equations, viewed as equations for the undetermined dynamical parameters of the theory, which is the conformal weights and oblique coefficients, given that they are over-constrained, perhaps they will fix the spectrum entirely. Of course, you have to give me something. You have to make some small dynamical assumption. For example, you may be interested in a theory that has a certain number of relevant operators, a certain number of operators whose dimension is smaller than the space-time dimension. You may be interested in a theory that has a certain global symmetry and assign the relevant operator different quantum numbers global symmetry. You may hope that under these very simple assumptions about the spectrum, there will be a unique solution of the crossing equation. As a physicist, you should really believe that, because that's a phenomenon of universality in statistical mechanics. We start from different lattice systems that have the same symmetry, and in the continuum limit, they're described by the same conformal field theory. So here is a dichotomy that I'm going to offer you. The traditional booster viewpoint, which is the one that I basically reviewed in the previous slide, would ask you to do what I said. You want to solve, presumably find a unique solution for given symmetry structure and given spectral assumption of these equations. Anyway, I hope the name bootstrap is clear enough. Everything you call in physics something is called bootstrap if you are under the delusion of getting something out of nothing. So here, the idea of getting something out of nothing is you make some minimal spectral assumption, and the equations are so constrained that that can be self-consistently solved. So the bootstrap is really a moniker that means self-consistent approach to solving the theory. And in 2 dimensions, in fact, this approach really does work. Conformal symmetry there gets enhanced to the full infinite dimensional symmetry of holomorphic transformations, and one gets an exact solution of many models. So, in fact, in 2 dimensions, what I said in the previous slide really is quite true. So there is a variable that controls the number of degrees of freedom of the theory that's known as the central charge. And for central charge smaller than 1, we have a complete catalog of unitary theories. And so if your lattice simulation tells you that the value of the central charge is some fractional number smaller than 1, and you know the theory is unitary, I can just go to the catalog and identify the theory for you, basically from pure thought. It's just that the algebraic classification is so rigid that there's unique physical possibility. The model bootstrap approach, which was started by this 2008 paper, uses a more subtle incarnation of the idea where you don't hope to solve for an exact equality where you determine everything analytically. Rather, you use the bootstrap equation to derive inequalities for this data, and this is a plot that we've seen recently, no doubt, where you see that by a very set of minimal assumptions, such as the existence of a couple of relevant operators in this Z2 symmetry, you corner precisely the three-dimensionalized model. So today, just to change the pace a bit, because you've seen the numerical bootstrap already quite a bit in this series of talks, I will focus on the first strategy. Rather remarkably, even in higher dimensional theories, thanks to the power of supersymmetry, we can solve things exactly. Unfortunately, not for the full theory, but for some interesting subsector of it. And if you have enough supersymmetry, which is equal to 2 in 4 dimensions, or 2, 0, and 6, you can identify a special set of operators, which I'm calling BPS, that very schematically are invariant under Q. Q is a very schematic way to denote a supercharge. So you have some operators that, in some very schematic sense, are preserving some amount of supersymmetry. And the operator algebra, I'm claiming, for this particular set of supersymmetric operators, when you position them in a plane inside the full-dimensional space-time, and this plane is parameterized by coordinates z and z bar, have a much simpler operator parallel expansion that only involves their meromorphic coordinate z and w. So not only this looks like two-dimensional conformal field theory, it's even simpler in two-dimensional conformal field theory. In two-dimensional conformal field theory, you have two-dimensional operators, but they would depend both on z and z bar, w and w bar, and this is just the holomorphic piece of the two-dimensional conformal field theory, which is known in physics as a chiral algebra and in mathematics as a vertex operator algebra. So to summarize the claim, we can identify, we can carve out with cleverness. I mean, the truncation is quite complicated. I gave a technical talk on this, which I believe has been recorded, where I explained this in much more detail. But with some cleverness, we can carve out this sector of the theory that is closed under operator parallel expansion and obeys a much simpler version of the operator algebra. And so the upshot is that in a lot of examples, the bootstrap equations for this sector are still very non-trivial, but solvable. And we can really implement this bootstrap the way I said it in the first incarnation. Make some minimal spectral assumption and just solve. Find exact equalities. Given that, at least at the moment, and I'm skeptical that this will ever change in the future, the abstract approach is the only thing we have for the superconformal theory. Let's see how far we can get. And we can get actually quite far. We know enough about the spectrum of the theory, for example, from string theory considerations, to have a plausible guess for at least a subsector of what the BPS operator should be. And using that minimal input, we can identify this chiral algebra of BPS operators with a vertex operator algebra had been discussed previously. In fact, it's the famous so-called WN algebra. And using this trick, we can compute the three-point function of one of the BPS operators exactly for any finite element, which is really a new result that tells us something about the deep quantum regime of the theory. And rather strikingly, this is a rather elaborate calculation. In the large n limit, this three-point coupling takes an explicit form, which is, in fact, in exact agreement with the holographic calculation in supergravity. And so this captures the leading nonlinear term in classical supergravity, and we obtain it purely from algebraic considerations. Now, in principle, although apparently this will involve some work, and we haven't done it yet, you could, since we have the exact results for finite n, we could systematically compute the one over n correction to this result and learn something we absolutely don't know at all, which were what are the quantum and theory corrections to this semiclassical duality result.
So you think it is out of the fourth term or something?
Sorry?
Do you think it is out of the fourth type terms in the M3 context? Or?
The leading correction would capture those. But that's, of course, easier said than done, because these out to the four terms are only known in a very schematic form. All the fermionic partings have not really been fully worked out, to the best of my knowledge. And so you will have to really work extremely hard to write down the entire set of terms on idea 7 times S4 and a strat, the leading 1 over whatever it is, n to the 5 half correction, or whatever it is. And then beyond that, all bets are off, because then you start learning about higher derivative corrections in M-theory. Now we can play the same game for our favorite trinion theory, and again, we know enough about the BPS spectrum. It's quite intricate. The BPS spectrum comes in certain antisymmetric representations of these 3 flavor groups. And we can, for the first 2 cases, it's relatively straightforward. Already the 3T case that appeared in the previous slide is already something quite exotic, the E6 squared algebra. And for T4, you find an incredibly complicated system of bootstrap equations that very miraculously admit a unique solution only for the very specific value of the central charge, the very specific level. Everything is extremely fine-tuned. It's a completely magical new solution that gives you an exception on a W algebra. And algebraic consistency, again, is miraculously obeyed and teaches about new dynamical information. And this game is so complicated that we have only pushed, in fact, this was done by my students in a nice way they wrote on their own. And beyond that, we still don't know what to do. Okay, so I realized that I'm, how much time do I have?
Well, nominally you should be finishing in a few minutes or an hour.
Okay, so this...
I would suggest, I mean, I think it's really good that we've been having these, these kinds of discussions, so I would suggest, don't try to race through, but just...
No, I don't.
We have a discussion tomorrow as well. I mean, it's been this long because of all the discussions, so...
It's okay. I'm actually getting towards my ending. Well, almost. I have 9 more slides, but they will go fast. So I promised to tell you a bit more about this other viewpoint, which is consistency in theory space. And in fact, this will now reveal a little bit the secret of this whole story, because, again, you might be tempted to dismiss at least some of this as a bit esoteric. These funny trinion theories and then 6 dimensions and why a little bit of this and a little bit of that. And in the next couple of slides, I will show you that if I move in a different conceptual dimension I haven't explored quite yet, it's all part of a beautiful coherent structure. And so from this, as in many things in our field, we have to go back to Witten, a famous insight that he had in 95, that 6 is equal to 4 plus 2. And so he said, let's take this 6-dimensional theory that we know and love. Well, we didn't quite know it quite yet in 95, but he already knew enough of it that he had the idea of considering the theory compactified on a torus and float the infrared. Now, since you start from the maximum supersymmetric theory in 6 dimensions, it is not so surprising that if you compactify the theory on 2 flat dimensions, you're not breaking any supersymmetry, and so you flow on the maximum supersymmetric theory in 4 dimensions, which is n equal 4 super young units. Now, the theory you started with had no continuous coupling, it only had a discrete coupling, but the torus very much comes with a continuous parameter, which is the shape of the torus. I mean, you're flowing to the infrared, so any information about the volume of the torus is lost at low energies, but the information about the shape is retained. And you will recall that the torus can be understood as you're identifying points on a lattice, and so there is a modular parameter tau, but which basis of vectors you choose on the lattice must be material, and different choices are related by an SCFT transformation. So the shape of the torus is really not parameterized by tau, by tau modeled out by SL2Z. And so we can argue that in the low energy limit you are getting SUN. The n of SUN is the same as the number of N5 branes. Super Young mutes with gauge coupling tau, and now we have a beautiful geometric picture of S duality. From the higher dimensional viewpoint, this is nothing but modular invariance of the torus. You may not find this picture entirely, I mean, of course, this is not a proof, but it tells you that if you had an intrinsic quantum definition of the 2-0 theory, this really would be the way to go towards the derivation of S duality. And Gaiotto in 2008, standing on the shoulders of giants, said, well, why do I have to limit myself to this boring shape, which is a torus? Let's take a more complicated surface and possibly decorate the surface with these blue dots. The blue dots can be given a precise meaning as certain boundary conditions. But anyway, let's ignore the dots for a moment. We have a surface now of higher genus. This surface will have a shape parameterized by a more complicated set of parameters which are identified with the complex suction moduli. And now, given that the geometry is more interesting, I will break supersymmetry in half. I will get an n equal to 2 supersymmetric theory in 4 dimensions. And similarly to the SL2Z duality that I heard earlier, now there will be a modular group relating these complex parameters. There will be a discrete identification of the complex parameter, and that discrete identification will be understood as a novel type of S dualities for this class, for these theories. And here, finally, hopefully, comes one of the punchlines one of the at least explanation of why I chose this particular subject matter, both in my research and in this talk. Well, I wanted to make a movie, but I wasn't capable of doing that. From the point of view of this funny shape, the most general shape you can actually have is a pair of pens, which conformally is the same as a sphere with 3 dots. Because given a pair of pens, I can glue, we're given several pairs of pens, I can glue them with cylinders and construct the most general Riemann surface. In fact, I can glue them backwards, so I can have something like this, glue them the torus, and then glue another pair of pens here in the torus, so I can also do closed surfaces. And so the basic building blocks out of which I can construct any Riemann surface are a pair of pens, which is also known as a sphere with 3 marked points, and the cylinder. And the dictionary is as follows. The cylinder corresponds in the 4-dimensional theory to a gauge group SUN, and the 3-puncture sphere, these pairs of pens, corresponds to this funny marine monster with 3 legs I had earlier, where each dot is an SUN flavor group. So these marine creatures, rather than being exotic, contrived examples, are in fact the basic building blocks of a generic theory that you can obtain from the 2,0 theory by compactification. And this picture now can be used to understand all possible dualities for the theories that come from 6 dimensions in this fashion. And this is a very powerful idea because, again, you have this idea of the generation of the surface as this neck of the surface becomes very long. This pictorial operation of decomposing the surface into 2 pieces corresponds, in the field theory, to taking this cylinder very long, which is interpreted as the gauge coupling becoming small. And so this is one duality frame. I decompose the surface in this region, one coupling becomes small. I get a certain Willy couple description. But I could decompose in another region, and another coupling becomes small, and then I have another semiclassical description, and they are related by dualities. But now what you must then observe is that physical observables, for example, the Witten index of the theory or certain BPS quantities of the theory, must be compatible with the rules that follow from this gluing of surfaces. And this is, in fact, so constraining that supplemented with some simple boundary condition for what happens at Lagrangian special cases enough to completely determine the observable. And so I have really only 2 slides. I don't have time to do justice to them, but I just want to flash them. This is some work, in fact, I did earlier, in the last, this 4 or 5 years ago. You can associate to this class of superconformal field theory their Witten index, but it's a very sophisticated version of the Witten index, which is refined by a bunch of parameters that take into account various geometric parameters of the twist, and the flavor fugacity is A that coupled to the flavored symmetry. And these are a very complicated object which can be computed in Lagrangian example in terms of integrals, matrix integral involving an elliptic gamma function. And just by this simple picture of the gluing, we could calculate this index for this entire class of theories, which gives us an infinite amount of information on their BPS spectrum. Okay, so we are having a lot of fun. This is a gold mine of exam results in mathematical physics. I did not talk at all about the numerical bootstrap, which was track 2 in my dichotomy of whether you want to solve or you want to carve. Today I was solving, another day I will be carving. And the carving, we do it in various dimensions with various amounts of supersymmetry. And I just want to leave you with this picture. We believe that the simplest 2,0 theory, the simplest non-trivial one, which has n equal to 2, the one corresponds to 2 branes, is at this corner. So you should take this picture as the analog of the picture I had earlier about the 3D Ising model. And finally, couldn't resist. So this is again some notion of carving. You can see it in action. As you increase the order of approximation, theory space gets reduced more and more. So what's outside this golden, it's really golden because it's, as I said, it's a gold mine. What's outside gets excluded, what's inside is allowed, but we have evidence that the true theory lives at this corner. Thank you.
So in your plot, was that the lowest dimension operator was dimension
Which one?
6.5, the previous area?
Yeah, so I should explain it. I mean, of course, I didn't explain what it is. So here I'm looking at the 2,0 theory has a bunch of protected operators. Those we can actually solve for completely using this idea of the chiral algebra. So now I'm looking at the non-protected. Well, again, what protected perhaps is also a misnomer here because there's no coupling, so it's unclear what protected means. What I should really say is BPS versus non-BPS. I'm looking at the non-BPS spectrum, and I'm looking at an exclusion plot where here I'm plotting the first non-protected scalar, the lowest dimensional protected scalar, and here the second one. And I mean, we have several overlapping pieces of evidence that say that something very special for the theory with 2 branes. In particular, we can put a lower bound on the central charge of the theory, and we find that the lowest allowed value of the central charge numerically converges to the value for theory 2 branes. So in some sense, within numerical, if you believe this kind of, well, as I emphasized another time, These numerical games are rigorous in the sense that you put bounds which are true, but you may not have reached the optimal bound. But if you believe that the optimal bound is going to be converging where it appears to be converging, then we have proved that the M2 brane theory is the one with lowest central charge. The answer, the M5 brane with 2 branes.
Any other questions? So we will have an open discussion tomorrow at 1 o'clock. So that would be another opportunity to ask more questions. We asked quite a bit during the talk. So let's thank Leonardo again.